Hello, welcome back. We are now starting chapter 7, which is analytic trigonometry. Now, in the past two chapters, chapter 5, in which we introduced the trigonometric functions, and then in 5 and 6, what we have been dealing with is mostly the geometry of these trigonometric functions. In this chapter, we will deal with the algebra of the trigonometric functions, and for that we need to readdress the fundamental identities that we have seen before. So we start with the Pythagorean identities. The first one, these first three identities, or they are, well, you see the equal to sign, but yeah, they are equations, but special kinds of equations which are true for any value of the variable. Like most equations that you solve, they are true for certain numbers or certain values of the variable, but in this case they are true no matter what x value you pick, real number x, they are true. So these are called identities. The first three are basically the called the trig identities, the Pythagorean identities, and the reason is because they can be thought of as coming from the Pythagorean theorem. And I think I have shown you this before. So if xy is a point on the unit circle, so on the unit circle, let's say the point is in the first quadrant. It doesn't matter on which quadrant it is. So if I draw a perpendicular from here, and if the coordinates of this is xy, then this side is x, this much, and this much is y, and this one will be 1 because the radius is 1. So you see x square plus y square is equal to 1. That is the Pythagorean theorem which we can apply here, and it gives us this identity first. Also, if you recall, we said that x square plus y square is equal to 1 is the equation of the unit circle. Now, because x is cosine and y is sine, but that's how we define them on the unit circle. So in place of x, you can write cosine, and in place of y, you can put sine, and we get this identity, which is the first Pythagorean identity. Now, from this, we can get the other two. How? Well, first thing, look at the identity. It is sine square plus cosine square x is equal to 1. If we divide the whole equation by cosine square, so each term will be divided by cosine square. So this first term becomes, I can write it as sine of x over cosine of x whole square. The second term becomes 1, and the term on the right of the equal to sign can be written as 1 over cosine x whole square. Now this term is tangent x and then whole square, so we can write it as tangent square x plus 1, and the term on the right is 1 over cosine x whole square, but 1 over cosine x is secant x, so we get secant x whole square or secant square x, so we get the second Pythagorean identity. In the same way, you can get the third one, but now this equation, the first identity, sine square x plus cosine square x is equal to 1. Instead of cosine square x, now divide by sine square x, and you get this third identity. The other types of identities that you need to review or recall are the reciprocal identities, which we already saw in chapter 5. So secant x is equal to 1 over sine x. Secant x is 1 over cosine x, and cotangent x is 1 over tangent x. But from here, you can also see that sine x, that 1, or maybe I should say 1 over cosecant x is equal to sine x. So it means if you take the reciprocal of both sides, you get that. In the same way, 1 over secant x will be equal to cosine x. And same thing about this one, 1 over cotangent x will be tangent x. Also, we have these extra, and this is coming from the definition, because the tangent was defined at the sine over cosine. So, and cotangent is cosine over sine. Another kind of identities are what we call the even odd identities, and these according to these, sine of negative x is equal to negative sine x, but cosine of negative x is cosine x. And why do we call them even odd? By the way, tangent of negative is also negative tangent. So you see, it looks like we have taken the negative sign out from here, but that is not the case. We cannot do that. We cannot pull out the negative sign. We are not multiplying here. So how did we get this out, the negative sign outside, and why don't we have it over here? Because these are the definition of, if you recall, the even functions and the odd function. So what is an even function? So we say f of x is even function if f of negative x is equal to f of x, which means if you have the value of f of negative 2, for example, should be the same as the value that you have at 2. And this is not just one number, it should happen for all x in the domain. This is, for example, and in the case of odd functions, we have f of x is odd function if f of negative x is equal to negative of f of x. So in other words, if I have f of minus 2, this is the same as negative of f of 2. So if you look at the graphs of these functions, so let's say this is negative 2 and this is 2. So if the function has the value over here, for the even function, the value at negative 2 will be up here as well, the same height. This is for the even. Okay, now for the odd case, if at 2 the value is up here, then at negative 2 the value should be down here. That's what even and odd functions tell us. So that's why we call them even odd. And another way to look at it is, look at the unit circle, and let's say you have some here and this is x, or you can say this is x. Then what is this? This will be negative x. So if you have cosine of x, the coordinates of x are, let's say a, b, then the coordinates of this will be a, negative b. So see, now on the unit circle, the point is AB, so which means cosine will be the first coordinate, the x coordinate. So cosine of x is A and cosine of negative x is also A, but sine of x is B and sine of negative x is negative B. So that's how you can think of it. Anyhow, we can now use these identities to simplify complex trig expressions and verify trigonometric identities. And that is what we are going to do in this chapter. There are some other identities which we can recall by observing the values of the trig functions, but they will come along as you see, and some of them you will have to memorize. Now the first situation, which if you understand how to do this, the rest of the sections will become easier. So to simplify a trigonometric expression, we will use algebra, which means we can use factoring, we could be taking common denominators, we could be multiplying top and bottom by the conjugate, this type of stuff that we have been doing in algebra. And also along with this, we might need to use some fundamental identities that I mentioned above. So the basic principles of simplifying trigonometric expression are that if you see addition or subtraction of fractions, you should take the common denominator, look at the expression as a single fraction, and then apply maybe some identity or some algebra might be needed. Now always look for factoring. So that is the first thing that you should do when you see an identity. If you see a mixture of sine, cosine, and cosecant, secant, or tangent, cotangent functions, then change everything into sine and cosine and then try to simplify things. Now, if you see an expression of the form 1 plus sine x or 1 plus cosine x or 1 minus sine x or 1 minus cosine x, then we need to multiply by the, you can say conjugate or the opposite. The top and the bottom must be multiplied together. Now, if you see an expression of the form 1 minus sine x or 1 minus cosine x in the numerator, then we have to multiply by the opposite, 1 plus sine or 1 plus cosine. And then remember the other form of the Pythagorean theorem can be written. So let's look at some example here. So it says simplify the following expression. So looking at this one, can you see there is as addition of fractions? Now we cannot simplify this like in this form, any of these, right? We cannot simplify this one separately, we cannot simplify this one. Well, we can write it as tangent t, right? But how will that help? So what we should do is take the common denominator. So what is the common denominator? Will be cosine of t times 1 plus sine of t. So that the top will become sine squared, sine of t multiplied by 1 plus sine t plus cosine t into cosine t or cosine square t. Now we distribute and we get sine of t plus sine square t plus cosine square t over cosine t into 1 plus sine t. Okay, so now what? If you recall now, this gives us, we can use the identity. So we get sine of t plus 1 and then divided by cosine of t times 1 plus sine of t. Now this factor cancels that factor and we get 1 over cosine t. That is what is left, but that is secant t. So that will be our answer. So this is how we use this simplification. Next one, well, here you see there is cosine x, then we have cosecant and cotangent. So since we have cosine and along with these two, so we should convert these two into cosine and sine. So this can be written as cosine x into secant is what, 1 over sine x, and the cotangent is cosine x over sine x. Now try to simplify. We basically have top is cosine x over sine x and the bottom is also cosine x over sine x. So we basically get 1. Looking at the next one, there is no fraction, so we cannot take the common denominator. We have just cosine and sine, so what can we do here? So think factoring. So we can factor out the cosine x. What is left is cosine square x plus sine square x, but cosine square x plus sine square x is 1. So we basically get cosine of x because this quantity is 1. Okay, so next 2 I will let you guys try, and then I'll come back and see what, show you the computation simplification, and then you can check what you guys got.